Now we will go to the third one. So the third one is the practical one. We are going to plug into all the parameters, and try to see what kind of final result we can have. So this can give you a little bit physical feeling, okay, beyond the equation we already have in the past lectures. So to get a physical feeling can help you on to build up your own intuition. Because for design, if you count all the equations, it's not easy because too many equations over there. So sometimes you need to build up your own intuition to help you to speed up the design process. Even though the first approach is not correct, but it may closer to your final results and easier for you for your future adjustment. If at the first time you make a decision is too far away from your final goal, that will be very difficult for you to do adjustment actually. Okay, so the first approach is sometimes important. So now we give it the first approach. So now we design a accelerometer. The structures you are familiar with already. So remember we have a proof mass here, okay, and a cantilever here, two cantilever to make the balance. So on the cantilever we have two sensors, okay. The other two on the silicon substrate. So these four circuits, these four resistors form a Wheaton bridge. Okay, as a circuit we designed before, Wheaton bridge. So only these two have a variation of piezoresistivity. The other two, the resistance will be constant because they are sitting on the top of a silicon substrate. It's not movable, okay? But for these two, during the cantilever bending, so the length of the resistor will extend, will change the length, and then change the strength, and also get a signal, okay, the strength signal from the cantilever beam. So these two are the sensor for getting signal. But remember, they are not designed at the same size. They are designed in opposite position. Okay, why? Okay, let's come back to the Wheaton bridge. Remember, two sensors is on opposite position. It's not on the same position because when we have the cantilever built up on the top, they are symmetry to each other. So when your proof mass bending down, that means the extension. It's compression. Your sensor is on the bottom, right? So it's compression. So the resistance feel the compression, okay, from the cantilever beam bending. So if both of them are compression, that means the resistance is reduced. Compression, reduced. Resistivity is reduced here. So if we reduce the resistance here, the voltage here will be increased, right? On the right hand side will be increased. You also decrease the resistance here. So the voltage here will be decreased. So the V plus will be decreased and V minus will be increased. So you get the minus voltage here. Okay, the delta V, minus voltage here. But if you put the resistance on the top, the resistance, the voltage here will be the same, right? They won't change. So you need to consider to put them in opposite position, okay? Not put on the same symmetry position. That will be not correct, okay? Remember the design. So you can change this Wheaton bridge, okay, onto the top of this real layout. So two on here and two on here. So the input voltage will be here. So input voltage will go into one of the sensor and then go to another, that's the reference resistor. The other side will go to the reference resistor first, then go to the sensor. So you can see these two, one is on the top, the other one is on the bottom, okay, of the bridge. It's okay? Yeah, so the signal comes from here, the voltage comes from here, and the current goes through the first resistor and go to the second resistor and go to the ground. That's one side, right hand side. Left hand side, the current going through the reference first, then go to the sensor the second, then go to the ground. Okay? So can you imagine that? It's okay? 可以想象吗？这是一个 Wheatstone bridge. OK? 好，从它的这个 current 从这边流过来，流过第一个 sensor， 再流过一个 reference 的 resistor， 然后到 ground。所以右边的话是先经过 sensor， 再经过 reference 的电阻。左边的话呢是先经过 reference 电阻，再经过 sensor， 然后到 ground。好，一个右一个左一。Okay, then the thickness for the cantilever part is 3.83 micron, and including sensor, and without sensor, 3.35 micron, the thickness. Okay, and the proof mass of the plate, the thickness is not very thin, very thick. It's only like close to 6 micron. So in your homework, you want to increase the proof mass, increase the responsivity. Not only the thickness of these many layers you can stack together, but also you can consider to put some kind of proof mass, a silicon substrate on the bottom to increase your proof mass, the structure. Yeah, because increase the mass, you can increase the responsivity. Okay? Okay, so now after, if now we don't have the underneath a silicon block, we have only the plate here. So now we will calculate some kind of important parameters. First one is the proof mass. The proof mass will be, for example, we have a 500 micron of the length, and the thickness is 6 micron. And the proof mass, the width and the length is the same. They are the same. They are 500 micron. Okay, it's like a square. So that's for proof mass. For cantilever beam, we have 20 micron for each. So totally we have 40 micron, the beam width. Oh, sorry, the length. Length, LB is the length. Oh, sorry. The length is 20 micron. It's like the width. The width is 20 micron as well. So it's like a square thing. It's very strange. Also square things. It's quite small. But you can extend your own version later on, okay? Here we got a square cantilever beam, square shape. Length is the same as the width, 20 micron. And also we have the thickness, okay. Another thing is the thickness, A is a 3.858 micron, the thickness of the beam. And another importance in the Z. Z means the position of your sensor, the distance between the sensor to the neutral surface. Remember, if we put the sensor as far away as possible, we can get a more signal, right? But for here, we have not much choice because when we stack those silicon dioxide together, the polysilicon sensor will be arranged here, is fixed position. So when we calculate the position from the neutral surface to this position, it's only 0.865 micron. Yeah. So if you are able to put the sensor to outside this region, for example, some people in the past, they try to use in the single crystal silicon part as a sensor. So you can take some material from the bottom, stick on the bottom as a sensor. In that case, our distance can be much longer. It's become like a 1.7 something. So the distance will be twice as the current distance. So the signal can be increased twice, readily. Okay, you understand? Polysilicon is here. It's not far away. It's only 0.8 micron. But if you put a single crystal silicon on the bottom, okay, because on the bottom we have a single crystal silicon substrate, so you leave a small portion here as a sensor, you can readily increase the distance of Z by twice, okay? But your homework don't do that, okay? Your homework does not allow you to do that. I'm talking about in your project, real project, in your research, you can consider to do that, okay? But in homework, try to use in the current, configuration. Don't change it too much, okay? And the Young's modules, actually we have it's a composite material. We consider a lot of different materials. So we're using one, for instance, roughly seconds Young's modules to estimate. So it's close to 10 to 11 Pascal. It's not very accurate. We just give us some estimation. Okay. And the piezoresistor part, the sensor we're using polysilicon. So the gauge factor we're using 20 is a typical number. Remember, if we use a single crystal silicon, this can be 200. It's not 20. The gauge factor can be much larger. But if we use a metal, it's only 1.6. The gauge factor is quite small. Okay, so that's why we are using the piezoresistive material, the polysilicon or single crystal silicon, because they have a high gauge factor. And we consider to choose the starting resistance as like 1 kilo ohm. You are familiar with this value already, because in the previous homework, we asked you to design the resistors close to this value, right? So you are familiar with this value. But now you know why, because if you have a higher value, you have a higher noise level. Later on, you can see. But if the resistance is too low, the accuracy won't be high. That's another consideration. Yeah. And also the length of the sensor, because we have the cantilever being only 20 micron in length. So our sensor can be not more. Okay. So we design the sensor distance, the length is 20 micron. So it's a banded sensor. So you take only like half of the cantilever beam to occupy half of the cantilever beam to arrange the sensor. Okay, 20 micron. Okay, this is a piezoresistor polysilicon. Now we go to the detail calculation. So for the proof mass, it's quite small. It's only 3.58 microgram. So it's quite small, microgram. Okay, so it's quite small. And for the moment means the acceleration times mass. So it depends on the acceleration. So the acceleration has been normalized by the gravity. Okay, gravity acceleration. 它已经被重力加速度这个叫做叫什么normalized 叫做正规化了。OK， 好，就是它是看我们这边 GAC 是看是它的几倍，好，是重力加速度的几倍的意思。好，我们用重力加速度，一个重力加速度叫做一个 G， 好，来去做计量的计算。好，不是加速度哦，是重力加速度。So the GAC means how many gravity acceleration we have. So this value has been normalized by the gravity acceleration. Gravity acceleration is 9.8 meter per second square. Okay. Okay. So the mass times the acceleration and times the arm. That's the moment we get. So the moment will be this value times the acceleration. How many gravity acceleration we have? It's a piconewton range, very small. Piconewton meter range. It's quite small. Then the momentum inertia is this value 10 to minus 22. Okay, it's also very small. And the strength. So the strength, when we put it into the equation here, we kick that the strength will be this much. So consider the maximum strength 1%, right? So here we got if we have only one gravity, so the strength got the final result will be 6 10 to minus 8. Okay, it's quite small. It's like a millions percent. 就百万等于是这10的80分之一。It's very small strength, very small strength. So if we consider only gravity of acceleration coming into the system, maybe we can only barely measure the signal. We will see later. We don't understand. We don't know now. Yeah. Okay. So the strength is quite small compared to our maximum strength, 1%. It's like a 5 orders magnitudes higher, lower, right? maximum strength is 1%. Here, if we have 1 gravity coming into a system, we got a strength 6 times 10 to minus 8 is around like a order of magnitude lower. 就是五次方比它小5次方，很小。Then we consider resistance change. It will be the gauge factor times the value and times our strength. There will be this final result. Resistance change is also very small. Okay. Then we got the voltage. The voltage will be 0.3 times acceleration times our voltage we provide here. So if we provide like 10 volts, we got the 3 times the acceleration microvolt. Okay. So 1 acceleration give you like a 3 microvolt. Microvolt is a very small signal actually. Usually the noise level is around like the microvolt range. So if I have 1 acceleration, I think 1 gravity acceleration, I think is barely can do the measurement. The responsivity, final responsivity will be 3 microvolt per acceleration. Okay. The G means the how many acceleration you have. So microgram per acceleration. So 3 times the voltage you have. So if you give it like 10 volts, you got a 30 for this responsivity value, 30 microvolt. But if you got like 100, you got a 300 microvolts. So the responsivity will be higher. Then the maximum deflection will be around like 18 nanometer. It's quite small. Maximum deflection. If you have a 1, depends on acceleration. Okay, per acceleration you have only a couple nanometer, tens of nanometer. The spring constant here is quite stiff. Yeah, it's around like 5,000 something. Okay, so that's why the maximum deflection is so small. Because the system, the spring is very stiff. It's not easy to bend. So when you have a gravity acceleration, the bend is only a little bit, only like tenths of a nanometer, not very high, because you have a strong spring. So you want to increase the maximum deflection, increase the sensitivity, responsivity. You need to consider to lower down your spring constant. Okay. Okay. So in the next example, actually I will give a lecture after the second midterm. We will try to design a smaller spring constant, so the spring constant can be lowered down to like close to 1. Okay, 1,000 times smaller, so that can give you better sensitivity. Then squeeze fin damping. Consider the dynamic system. So it's this value. Okay, we are using the distance 100 micron, and the radius we consider is a 500 micron square, so we're using 250 micron diameter, the radius as a similar structure to calculate the squeeze fin damping value. So now the resonant frequency omega n equal to spring constant over your mass is like a 200 kilohertz. It's pretty high, 200 kilohertz. To your surprise. So that means the window has been opened up to a very large window. Yeah, so the frequency response is the higher. The reason for the frequency response is that high is because we have very strong spring here and a very small proof mass. Okay, so that's why the response, the moving speed is very, very fast for the system. So when you have a very high frequency signal coming to the sensor, you still can do the detection. However, in our system, you want to use this for detect the car accident. It's not useful. For car accident, the frequency response usually is lower than kilohertz. Couple hundred maybe, from tens of hertz to kilohertz. So you can see if you want to use this sensor for the car accident detection, I think it's overkill. Yeah, it's too much. And also you introduce a lot of noise into the sensor. It's not good. So in your design, you need to try to reduce this number. You don't need to that much. So that's why in the specs, we give you like a 5 kilohertz or something. That will be enough. Okay. Now we come to the important part, noise. Remember, we have two parts of noise. One is the TNEA noise, is a mechanical noise. So the value corresponding to the acceleration is like this. Okay. So the acceleration, you don't have any feeling, so you need to transfer this acceleration into the voltage value. So this value need to times with the responsivity. Okay. So we have a responsivity here. Responsivity is this value, 30 microvolts per acceleration. Okay. Okay, so we need to times this value. So we got the voltages around like also the bandwidth. We need to times the bandwidth as well, per square hertz. And for junction noise, for each resistor, we have this much noise times the wavelength. So remember the total noise, we were using noise power to add them together. So the noise power for acceleration, corresponding to acceleration, will be this part times the frequency response. Frequency response is 200 kilohertz. We times 200 kilo here, and got the first one. And the rest, we have 4 resistors, as we can see. So each resistor, we're using the junction noise to divide by the responsivity. So the junction noise equivalent voltage divided by the resistance, the responsivity. We end out, we get the value become acceleration, equivalent noise. 就是把它换成加速度了。我们现在是换成加速度端，好，不是 output 端，是 input 端。好，看这个 noise 相当于多少的加速度，因为我们现在是要量加速度，所以我们要知道最小可以量到的加速度是多少。OK。So you add all of them together, you end up to find out your noise, the noise level, noise equivalent acceleration equal to 0.2 gravity acceleration， 就是它只有1/5的重力加速度，你可以量到的1/5的重力加速度。1/5重力加速度就是就是9.8除上5，大概差不多是，抱歉是4，这个0.2是4/4的重力加速度，等于你的用10除以4好，就是就一样嘛，0.25对，就1/4的重力加速度，大概就是2.5个 meter per second square. Yeah, so roughly 2.5 meter per second square. The acceleration you can measure here. So the minima signal you can measure, the acceleration is 1/4 of the gravity acceleration. Okay, 1/4 gravity acceleration. So in our homework, we want you to design the minima acceleration is 0.01 gravity. So you need to move from this point down to a more sensitive part. So you can try to increase the length of your cantilever and increase your proof mass, the size of proof mass, and try to consider increase the thickness maybe, put some mass underneath something. Yeah. So you can start from this point to do some arrangement. Then we go to the several parameters like diamond range. So lower limit is we just has a calculation is 1/4 of the gravity. So that's a lower limit, the lowest signal you can detect. The upper limit will be the fracture of your cantilever. So there will be 9,000 gravity. It's pretty high. 9,000 gravity. So this range is around like the diamond range is around like 4 order magnitudes, 3.7 times 10 to 4 order magnitudes. So the range is quite high actually, quite large. The range, the diamond range. So from very low signal to top signal, you have 4 order magnitudes. So remember, in our homework, we want you to design the diamond range from 0.01 acceleration, the gravity acceleration, up to 100. It's also 4 orders of magnitude. Okay, so it's already it's like the diamond range is like a window for your workable region. So you can move the workable region from not that sensitive to the more sensitive region, but you still have 4 order magnitudes diamond range, okay, for your sensor. Understand? Okay, so the peak diffraction, if you have like a 9,000 G, the maximum diffraction will be 700 micron, okay. But remember, we already cut the bottom. For example, if we take all the material away from the bottom, so there will be 500 micron depth, maybe. So if you put something on the bottom, so that can be the protection. So you can never be, the proof mass will never go down to that kind of point until you break, because you have put some plate over there to protect the bending. Not that too much, okay? So 700 will be the peak diffraction, the breaking point at this 9,000 gravity. Okay, so that's the end of the this plugin. All the parameters give you some basic idea. So definitely, the current design is not fit into your final, right? Your final one is 0.1 gram gravity, up to 100 gravity, and I want you to put all the design into a smaller area, as small as possible, into like 500, I think 500 micron or something, in a small area, as small as possible, including circuit, everything together, into a small area. Okay, so try to, you can try to enlarge your geometry, but depends on what kind of geometry can give you the best, results. Like the length of your spring constant, I mean the diffraction of the beam means the cantilever beam, and also the proof mass. These two you can do some adjustment as well, and also the width. Okay, increase the width of the proof mass, also increase the volume and also the weight of the proof mass as well. Okay, so you can play with those kind of parameters and try to work with them.